that for tracking, we need to choose an appearance model for my target object. We need to choose a transformation model and a similarity function to tell how similar the reference image is to the current image in the video. So given the parameters p from my previous frame t-1, we need to devise a strategy, a search strategy, to find the new model parameters p at the current time t. So the most simple approach is to do a simple, an exhaustive search on the neighborhood around the previous parameters p at time t-1. So in the case of the translation model, this means searching on a plus minus delta region around the position of the target object in the previous frame. So one may think that this is a very naive approach, but it's been used in a huge variety of applications, such as, for instance, monocular SLAM. So in the video here, you can see the horizontal and the vertical displacement of these salient points on the image are detected and tracked using the sum of square differences. And another alternative, a more intelligent alternative, is to incorporate more knowledge on the object's motion for improving tracking efficiency. So instead of doing an exhaustive search on a wide neighborhood around the object's previous position, which is often very computationally expensive, we can reduce our search using a priori knowledge on the object's motion. And we can even use additional information from external sensors, such as an inertial sensor or EM tracker, and fuse this information with our search strategy. So for this, we can use the classical Kalman filtering framework, or more sophisticated filters such as the particle filter. And another very popular search strategy, which will be the topic of our second part, is gradient descent. So if we choose a similarity function that is differentiable with respect to the tracking parameters and has a smooth and convex landscape around the best match, we can use gradient-based techniques to surf the gradient of the similarity landscape and find the optimal tracking parameters, the optimal parameters of my transformation model. And this is the case, for instance, of the SSD, the sum of square differences. Assuming that, in this example here, assuming that a green rectangle is my reference image, the result of the computation of the SSD score for this blue rectangle here, for a plus minus 5 pixel displacement around the optimal place of alignment, gives me this curve that we see on the right. So we can clearly see the convex and smooth nature of the SSD in this example. So what is the major advantage of gradient descent? Well, imagine we have a transformation model with multiple degrees of freedom, such as the projective model that we're using to track this board here. Using particle filtering or exhaustive search, which were the other methods we talked about previously in the previous slides, we would need to search through thousands and thousands of combinations in order to find the best transformation parameters. But with gradient descent, we can obtain these parameters with very high accuracy in only a few iterations. So it's a major save in computational effort. Okay, so let's do a quick recap. So far in this video, I've introduced a few appearance models. I've talked about transformation models, both rigid and non-rigid. I've mentioned a few similarity measures and also some search strategies. But it should be clear to the viewer that the tracking methods are basically composed of these four components, these four major components that we've introduced early in the presentation. So for instance, I could have replaced the intensity-based appearance model. So I could have replaced the set of pixel intensities by a histogram, and instead it would be much less sensitive to structural changes. But I could use a similar similarity function, such as the Bhattacharya distance, which is equivalent, or the Matsushita distance, which is equivalent to the SSD, and I would be able to track using the same gradient descent framework. So for instance, here I'm tracking using the famous mean shift tracker, and it's very interesting to see that we can derive several different types of methods in the literature based on this framework that we've presented in this introduction. So we're going to see some more details in part 2, and hopefully some code in part 3. So